And good evening everybody. And in this today's class, in this video, I'm going to explain how to solve the given differential equation of second order with q of x equals to tan x. And in this unit of higher order differential equations, we have 5 cases related to this kind of RHS, which we are going to denote by q of x. We have the 5 cases. The 5 cases are when we are having in this place, when we are having q of x equals to e power ax, that is case 1. When we have sin ax or cos ax here, we have case 2. And if we have polynomial or x power m, that is case 3. And if we have e power ax into v of x, that is case 4. And x into sin or x into cos x, that is case 5. But if we have new function, a function other than those 5 cases, like we have here tan ax, we can use in this case we can use either general method or variation of parameters to solve this second order differential equation. And in this class, I've taken the help of variation of parameters to find pi here. I'm not going to take the help of general method. And here first the method is the problem is actually solve d square plus a square into y equals to tan ax. And here the method is same. This is a second order differential equation, and for the given second order differential equation or higher order differential equation, the formula for complete solution or general solution is y equals to cf plus pi, where cf is called complementary function and pi is particular integral or particular solution. We have to find complementary function and particular integral, and we have to add both to find the solution of this kind of second order or third order or simply higher order differential equation. And here the way of finding the solution for this differential equation, d square plus a square into y, that is equals to tan ax. Here I'm going to take the help of variation of parameters. We can use general method, but here in this video I'm going to take the help of variation of parameters method. And the formula is same using variation of parameters also. Y equals to cf plus pi, and finding cf is same, but in finding pi we have a procedure related to method of variation of parameters. Now first I'm going for cf, and let us take the solution. Given d square plus a square into y equals to tan ax, let us take this one as well. And here I have written differential equation is this differential equation. One is of the form, here let us imagine a d square plus a square is f of d, and into y, that is equals to, let us take this tan ax as q of x, and that means this one is in the form of f of d into y, that is equals to q of x. And now if we compare this one with this f of d into y equals to q of x, we can have f of d equals to d square plus a square, and we can have q of x equals to tan ax. And now the complete solution of this differential equation is y equals to, you know this formula, cf plus pi. Let us take this one as 2. At the end I will find cf and pi, and I will substitute this equation 2 to get the answer. That is nothing but solution. And for cf, for complementary function, that which is first part of this formula, consider the auxiliary equation. We have to take the auxiliary equation. The auxiliary equation is f of m equals to 0. And now that implies we have f of d equals to d square plus a square. Therefore automatically f of m means in the place of d we have to replace m. That means we have m, if f of d equals to d square plus a square means f of m equals to m square plus a square. Therefore that is equals to 0. And here this is second degree equation. Therefore we are going to have 2 roots and 2 values for m, and we have separate 2 or 3 procedures we have to find the 2 roots of this equation. And here I'm using this procedure. Take it plus a square to other side minus a square, m square equals to minus a square. We have that implies m equals to plus or minus, if m square equals to minus a square, that implies m equals to plus or minus root of minus a square. Already you know this. If x square equals to a square, x equals to plus or minus a, already we have that. M equals to plus or minus root. Inside root if we have minus, that means we are going to have complex roots. Inside root, if you have minus, that means we are going to have complex roots. Therefore that implies plus or minus root in the place of minus a square minus 1 into a square, you can write in the place of minus 1 you can write I square into a square. I have written. That implies m equals to plus or minus root, you can write a square into b square as a into b whole square, therefore I into a whole square. That implies plus or minus square root cancel, and we are going to have plus or minus ia. That means we are going to have two roots. The two roots are plus ia and minus ia. That implies clearly to represent alpha plus I beta and alpha minus I beta in the form of alpha plus I beta and alpha minus I beta. I have written plus ia as 0 plus ia to show the real part. Clearly I have written like this, and I have written minus ia as 0 minus ia. These are the two roots we have, are the roots. Where if we compare these two with alpha plus I beta and alpha minus I beta, in the place of alpha we have 0, in the place of beta we are going to have a. And now this is the case related to having roots which are complex and different. These two are complex roots and different roots. These are two different roots, complex. In this case of having two different complex roots, CF equals to e power, this is the formula we have. We should have idea on these formulas. E power alpha x into c1 cos beta x plus c2 sin beta x. That implies CF equals to e power, what is alpha? 0. What is beta? A. Therefore I am going to replace those two, alpha with 0, 0 with alpha, into c1 cos ax plus c2 sin ax. This is the CF we have. This is the CF we have, which is the first part of our general solution, required general solution. And now CF we can write as e power 0x. 0 into x means 0. Anything power 0 means 1. Therefore 1 into c1 cos ax plus c2 sin ax means again we are going to have c1 cos ax plus c2 sin ax. And now this is CF we have. And now we are going for PI, which is the second part of this general solution. And now this, here I am going to start how to find PI using method of variation of pyramids. The method is, first we have to compare for every problem. If you want to use variation of parameters, this is the process we have. First find CF, and now next we are going to have this process. Remember, we are going to use variation of parameters for only second order differential equation. Therefore this is second order differential equation. Therefore hence I opt for a variation of parameters to find PA. Compare, now I am going to start the process to find PA using variation of parameters. Compare CF with the C1. Compare this CF with the C1 U of x plus C2 V of x. That implies if you compare this CF with this, in the place of U of x we have cos x, in the place of V of x we are going to have sin x. The term which is beside C1, that is C of x. The term which is beside C2, that is V of x we have. And now by the method of variation of parameters, the formula for PA, let PA equals to, this is the formula we have, capital A into U of x plus capital B into V of x. Simply in CF replace C1 by capital A and C2 by capital B. Write cos ax here, write sin ax here, like this. PA equals to A into, what is U of x? Cos ax. This is U of x. And what is V of x? Sin ax. This is the formula for finding PA using variation of parameters. To find PA using variation of parameters, we have to start the process like this. And now here, this is the PA formula. Already we know that PA does not contain arbitrary constant like capital A and capital B. That means we have to find the arbitrary constant should be there in CF only. Like C1 and C2 we have in CF. And now we have formula for to find capital A, this capital A. And we have formula to find this capital B value by using variation of parameters. And now before giving the formulas of capital A and capital B, in capital A and capital B we have the term u into dv by dx minus v into du by dx. Therefore first of all I am going to solve that term which is there in capital A and capital B. And now consider u into dv by dx minus v into du by dx. First find this value. What is u? U of x. u means u of x. What is u of x? Cos ax. I have written u. What is dv by dx? Dv by dx means v derivative with respect to x. That means this is the v sin x. This is the v sin ax. Take the derivative of v of x, which is sin ax, with respect to x. What is sin ax derivative? Cos ax into, let us imagine ax as x, therefore cos ax into ax derivative a. That is the derivative for sin ax, which is v of x derivative. Cos ax into a minus v into du by dx. What is v? This is v sin ax. Sin x are written here. And what is the du by dx means u derivative, cos ax derivative with respect to x. With respect to x. That means cos x derivative, what is cos x derivative? Minus sin x. Let us imagine ax as ax as x. That means cos x we are having, cos x derivative is minus sin x. That means minus sin x into ax derivative a. And now u du by dx minus b du by dx is this. And now let us take a here. A is here. A I had taken a as common. Therefore cos x into cos x, cos square x, minus into minus plus, sin into sin x into sin x, sin square x. Here ax, like treat this ax as theta. Cos square theta plus sin square theta, or sin square theta plus cos square theta. What is the value of this? 1. Therefore a into 1. That means first we have found u du by dx minus v du by dx, which is equals to a. And now I am going to find this capital A, capital V, which is there in Pi, using variation of parameters. And now this is the formula to find capital A. The formula for capital A equals to, I think it is clear, A equals to minus integral v into q of x by u into d by dx minus v into du by dx. Already, as I told, already we have found this value, which is there in A and B. And this is the formula to find A dx. That is equals to minus, I have written minus here. And now v, what is v? We have v of x equals to sin ax. What is q of x? Q of x equals to what? We have q of x. We have q of x, which is tan ax. I have written here tan ax by, what is, already we have found this, u dv by dx minus v du by dx, which is a dx. I have written v here, which is sin ax, q of x here, which is tan ax, by u into du by dx minus v into du by dx, which is already we found, which is a whole dx. I have written. Now simply we have to solve this integration, which is nothing but the answer for this capital A. And now here inside this integral, 1 by a is constant and is multiplying. Therefore take out 1 by a minus 1 by a, that is equals to sin ax. You can write tan ax as sin ax by cos ax, sin x into sin ax by cos ax, sin x into sin x, sin square x by cos ax dx. You should have idea on the formulas of tan ax. These are basic formulas. Minus 1 by a into here, we should be able to solve this integration. And now so to solve this integration, simply write sin square x equals to, you can write sin square theta as 1 minus cos square theta. Therefore I have written that sin square x as 1 minus cos square x. And now here in the numerator we have two terms, and by single term cos x, one term is 1 cos square x. And now two terms by single term means you can divide into two terms. 1 by cos x. What is 1 by cos x? 1 by cos theta secant x. Minus here we have cos square x by cos x. Cos square x, in cos square x you can cancel cos x, therefore we are going to have cos x dx. And now that is equals to minus 1 by a into, divide this into two parts. Divide this integration into two parts. Integral secant ax dx minus integral cos ax dx. Minus 1 by a is multiplying both of these parts. And now minus 1 by a into, and we have, since integral secant x dx equals to log secant x plus tan x. Let us imagine ax as theta. Integral secant theta d theta. Therefore here the formula will be log secant x plus, in the place of x what we have ax, log secant ax plus tan ax by the derivative of the term which we have taken as x previously. Ax we have taken as x, therefore ax derivative by ax derivative a. The derivative of the term which we have taken as x, which we have imagined as x previously. We have imagined x as x, therefore by ax derivative a minus. Second, cos ax integration will be, what is cos ax integration? Cos theta integration will be sin theta. Sin theta, not a minus sin theta. Derivative is minus sin theta. Therefore, minus. Let us imagine cos ax as x. Therefore, integral cos x derivative sin x, that means sin x, by ax derivative a into x derivative 1. Therefore, by a. You should have minimum idea on integration. How to find the integration formula. That means here minus 1 by a, LCM will be, for both of these parts, LCM will be a. Therefore, if you take the LCM a, and if you take out that 1 by a minus 1 by a into 1 by a square log secant ax plus tan ax minus sin ax. This is the e, capital A. And now I am going for b. And b equals to, by using variation of parameters, the formula for capital B is this. Integral, previously minus we have, now we are not going to have minus here, only plus. Previously in uv we have v here, and here we have u. Same q of x, and the remaining terms are same. q of x, denominator is same, dx is same. That is equals to, in the place of v we have u, in the place of minus we are going to have plus. That is equals to, write u. What is u? We have u, which is cos ax. I have written cos ax here, into, already we have discussed q of x equals tan ax, by, already we found this denominator u dv by x minus v du by dx. We found this, that is equals to here. And now a dx, and now 1 by a is constant, take out like we did in previous finding a, 1 by a, and here we can write cos ax into tan ax as sin ax by cos ax. Cos ax cancel, we are going to have sin ax dx. That implies b equals to 1 by a into, what is the sin ax? Sin x integration. Let us imagine ax as x, sin x integration minus cos x, that means minus cos ax by ax derivative a. By ax derivative a. That means you can write capital B as minus, you can take 1 by a into 1 by a minus 1 by a square cos ax, you can write. And this is b. And now substitute this capital A and this capital B now to find PA in this 3, which is PA equals to a cos ax plus b sin ax. Now I have written here, hence from 3, PA equals to a, this is a, this is a, this is a. I have written that a here, a, this is a, and into cos ax minus, actually we have plus, but b into sin ax, a cos ax plus b sin ax from 3. A cos ax plus b sin. What is b here? B is nothing but this. Actually we have plus, but plus into minus we have in b, plus into minus 1 by a into 1 by a square I have written into cos ax, that is b, into sin ax in the formula of PA. And now this is PA, and now I want to solve this. PA equals to minus 1 by a square into, multiply with minus 1 by a square, these two terms, minus 1 by a square into this term, minus 1 by a square into log secant x plus tan ax, minus into minus, plus 1 by a square into sin ax into cos x, 1 by a square into sin x into cos x, minus 1 by a square into sin ax into cos x, minus 1 by a square sin x cos x plus 1 by a square sin x cos x, cancel. Therefore we are going to have this term only. This is our capital, which is our particular integral PA. And now if you want complete solution formula is y equals to CF plus PA. What is CF? This is C1 cos x plus C2 sin x is PA. This I have taken as 1, for 2. Therefore from 2 complete solution will be y equals to, this is CF, C1 cos x plus C2 sin x, which already we found CF, and this is PA. This is PA plus, actually we are going to have plus here, but plus into minus PA means 1 by a square log secant x plus tan x into cos x. This is the answer, and this is the process to find any given differential equation of second order by using variation of parameters. Thank you.